Welcome to solverfy.
We are given a weighted graph, and we are asked to use Prim's algorithm to find a minimum spanning tree for this graph. So the graph is a graph on the vertices A, B, C, D, E, F, G, H, and I. And I don't have it pictured here, but it can be found in the book at exercise 3. It's very detailed, so I suggest that you just use the book to look at the graph. Now, to use Prim's algorithm, first, we want to just draw the graph with the vertices of the given graph and with no edges. So that's what we have here, A, B, C, D, E, F, G, H, and I. And then let's pick a vertex to be the root, say vertex A. This will be the root of our tree. And now, looking at the edges that are incident to A in this graph, we see that edge AD has the smallest weight. Edge AD has a weight, in fact, of 2. And so we'll add this to the tree in green. And now, in the next step, we have that there's still one edge incident to A and 4 edges incident to D now. And we have that the smallest weight of these edges is going to be 3, and this belongs to the edge BD. And since this edge doesn't cause a circuit, if we add it, we can of course add it to the graph. So we'll add BD, which has a weight of 3. In the next step, of all the remaining edges that are incident to A, B, or D, there's a lot of these. The smallest weight, which is 4, belongs to the edge BC. And if we add BC, we don't obtain a circuit, so we can add it to the graph. In the next step, we have all the remaining edges that are incident to the vertices A, B, C, or D. The smallest weight, which is a weight of 3, belongs to the edge CF. Now, if we were to add CF to the graph, it would not create a circuit. So we will add this edge to the graph. In the next step, with all the remaining edges that are incident to the vertices A, B, C, D, or F, we have that the smallest weight, which is a weight of 1, belongs to the edge EF. Now, if we were to add the edge EF, we would not create a cycle in our tree, or circuit. So we can add this edge. And in the next step, of all the remaining edges that are incident to A, B, C, D, and now E or F, we have the smallest weight of these remaining edges, which is 3, belongs to the edge EH. Now, if we were to add edge EH to our graph here, we still would not be creating a circuit. So this is a valid move under the algorithm. So EH is going to be in the tree. And in the next step, we have that of all the remaining edges that are incident to the vertices A, B, C, D, E, F, and now or H, the smallest weight of 2, belongs to the edge HI. Now, if we were to add the edge HI to our graph, we still would not obtain a circuit. And so this is a valid move. We'll add the edge HI. And now we notice that right now all the vertices A, B, C, D, E, F, H and I are all connected. The only disconnected vertex is G, and so it follows that we only need to have an edge incident to G. If you were to add any other edge, then we would cause a circuit and we no longer have a tree. So we have that the edge incident to the vertex G with the smallest weight is edge GH with a weight of 4. And so we'll add edge GH, which does not give us a circuit. And so we have a connected graph, and by Prim's algorithm, it follows that the graph is a minimum spanning tree. With edges AD, BC, BD, CF, EF, EH, and HIGH. And this is our answer.